We're going to talk about capacitance, the way we describe capacitors with the capital letter C. And the definition of capacitance is Q over V, the charge per unit volt. Units-wise, if the charge is in coulombs and the potential difference is in volts, the capacitance will be in farads, spelled with a capital F, named for Michael Faraday. And that's a good definition. It's not particularly transparent. I mean, if you haven't worked with capacitance before, why that makes sense is probably not obvious to you. So it is important just to memorize C equals Q over V. It's probably the most important thing to know about capacitance because it's the definition of capacitance. But let's talk about what you can do with capacitance, and first, just what it means. Let's think about a capacitor and putting some charge on it. If we put a little bit of charge on a capacitor, that builds up some field inside of the capacitor. And when that happens, that means that the potential difference between the two plates has risen from 0 to some finite value. Let's just remember briefly what we mean by that potential difference. Why do we know that there has to be a voltage in there? Well, let's remember the definition of potential difference, or the concept of voltage, comes from the idea of introducing a test charge into the area we're interested in and then moving it from one place to another. So if we take an imaginary test charge, we put it on one plate and we move it to the other plate by virtue of some external agent pushing on it, the potential difference between those two plates is the work divided by the magnitude of the test charge that we have moved. And so if there is a field in there, then we have to do some work against the field to move the test charge. The stronger the field, the more work we have to do. So if we add more charge to our capacitor, increasing the field in between the plates, then the voltage goes up. And the voltage goes up because the potential difference has gone up, and the potential difference has gone up because if we bring a hypothetical test charge and try to move it against that field, we're going to have to do more work. So every time we add charge, we add voltage, and you can see the voltmeter goes up. Okay, let's compare two different situations in which we might go through this process. Suppose we had two capacitors, one that's got really big plates and one that's got much smaller plates. If we add charge to both of these, the voltage goes up. We add the same amount of charge though. You notice the one with the smaller plates, the charge is packed closer together. If the charge is packed closer together, the field lines are closer together. When the field lines are closer together, there is a greater magnitude of charge. There's a greater magnitude of field. So if there's stronger field, if we have to move a test charge in that stronger field, we have to do more work. And so the potential difference between the plates of the two different capacitors, it's not the same. Right? In one of these situations, we had the same amount of charge as the other with the smaller plates. We had the same amount of charge, but that's going to raise, the field is going to go up more. It's also going to raise the potential difference more because if we try to move a test charge, we're moving it against a stronger field. So every time we add charge to these two situations, the potential difference does not go up the same amount. So these are two capacitors with different capacitance. We say they have different capacitance. We're going to describe the capacitance with the letter C. And in these two situations, adding a certain amount of charge does not change the voltage the same amount. A big capacitor, something with a lot of capacitance, is a capacitor where we can add a lot of charge without raising the voltage so much. So while this is a cartoonish version, the top capacitor, while it's both geometrically bigger, it also has a larger capacitance because we've put on the same amount of charge, but the voltage hasn't gone up as much. And if you remember, C equals Q over V. I should have that visually in here, but I don't. If C equals Q over V, if the voltage goes up more, that means we have a lower capacitance. Here are the steps for computing the capacitance of any arrangement of conductors. And capacitance depends essentially on geometry. It's a story about geometry. We think about charge along the way, but really geometry is what controls capacitance. And the basic steps, no matter what you're going to address, are that you draw the configuration of the conductors, that you hypothetically imagine that one of them had some charge Q. You say, if that were true, oh, not just one of them, the other one's got to have opposite charge Q. You say, if that were true, what would be the strength of the E field? And then you say, given that E field, what would be the potential difference between those two conductors? And then now you have these two things. You know the delta V and you know the Q, and that ratio is what capacitance is. So you compute the ratio C as Q over V. That's the idea. So we're going to walk through how you would do this for a parallel plate capacitor, meaning two plates that are parallel to one another, and our capacitor is going to have area A, and it's going to have a plate separation of D, and we're going to figure out what its capacitance would be. The second thing that we're supposed to do is to imagine the presence of a hypothetical Q. Remember that the whole thing is net neutral. So if we put Q onto one of these, a positive charge onto one of these plates, we've got to put an equal negative charge onto the other plate. And so that's what we're going to do. We're just going to say, suppose these two things had charges Q and negative Q. Next, we compute the strength of the E field based on our configuration so far. And we're going to compute the strength of an E field where we've got the top plate is charged up to some charge Q and the bottom plate is charged up to minus Q. We're going to start thinking just about the top plate. So to think about the top plate, we're going to just zoom in on the top plate and just say, all right, let's just think just about the top plate here. And so we've got a top plate. It's all charged up with lots of Q on it. And how do we do that? We use Gauss's law. So we remember that we're going to use Gauss's law, where Gauss's law says that the phi is equal to Q enclosed over epsilon naught. And what Gaussian can we use? Well, we want to have a Gaussian surface that goes through this top plate, and it can be shaped like a square or a circle or anything you want, and it's going to go through the top plate and come down to the below it like that. And it's going to enclose some of that charge. I'm going to use sort of a soup can shape, and my soup can shape is going to have some area lowercase a, and so that's also going to be the area of the top of the surface and the bottom of the surface, and it's also going to be the area of like the chunk of charge that gets punched out right there. And so now it's time for us to rewrite Gauss's law. We say, what is Q enclosed? Well, Q enclosed is going to be equal to the charge density right there times the area. Q enclosed is the charge density times little case a. Well, what's the charge density? The charge density is the charge on the whole plate divided by the area of the whole plate. So Q enclosed is equal to Q in the whole plate times the area of our Gaussian divided by the area of the whole plate. And let's talk about what about phi? What is phi? Phi is the degree to which that E field crosses the Gaussian. And so if that's our E field down here, and our E field is uniform in strength, and it crosses the Gaussian perpendicularly, we have the phi for the sides, which the phi for the sides we hope is 0, right? Because right here the field is just going right along there. So we have just the phi for both ends. So that's the E field strength. Phi for both ends is the E field strength times the area that the E field is passing through, and that's the area of the bottom plus the area of the top. So it's 2 times the area of our Gaussian. And we said the Q enclosed is sigma A, or Q little a over big A. And so now we're ready to go. We can calculate our E fields. The little a's cancel out. That's good because we made them up. Oh, I forgot my epsilon naught here. And so this tells us that the E field due to the top plate is equal to Q enclosed over 2A epsilon naught. So we just found out that the field due to the top plate is Q over 2A epsilon naught. The top plate makes field that goes away from it, right? It's positive, and it goes away. But the field inside here, the field in this area there, that we're interested in, is actually a combination of two fields. It's the field due to the positive plate plus the field due to the negative plate. Well, what's the negative plate do? The negative plate has field pointing toward it, right? And that means down here it points up. The negative fields point towards the plate, so it's doing this. Now notice what's going on. Up here, the positive plate's field and the negative plate's field, they oppose each other. And since they have the same magnitude of charge and the field strength doesn't fall off any, out here the field just cancels out. And down here the field just cancels out. But in here, the negative plate's field is pointing down and the positive plate's field is pointing down. So, and they have the same magnitude. So the field in here is going to have twice the field strength of the positive plate. So we can say that the E field in here is just Q over A epsilon naught. Our next job is to find out what is the potential difference between the plates. Alright, what is the potential difference? The potential difference, we know that delta V in general is equal to the opposite of the integral from one place to another of E dotted into ds, with both these guys being vectors. And so what that means is we're going to suppose that we were going to move a hypothetical little Q naught test charge from one plate to the other, and that an external agent is going to do the work to move that charge here and from here to here. And the question is, how much work is that going to require? Well, this is actually a really easy computation to make, because this integral is going to be easy to do because this E field is of uniform strength, right? What we're doing is we are moving through this E field which has uniform strength, and basically we're saying how far are we moving it, and we're going to find the area under there in order to find the work per unit charge. So that's actually really easy because the distance that we're traveling is just some distance d. And so in this case, we don't have a difficult integral to do. We can just say that delta V is equal to that E field times the distance. And we can write that as delta V equals Q d over A epsilon naught. Okay, now the final step. We want to compute C. That was the whole idea. What is the capacitance of this configuration? So we need to know Q and V, because C is Q divided by V. Well, what is Q? Well, Q is just Q. We made it up. We invented it. No big deal. What is V? What's the potential difference between the plates? Well, we computed that on the last step. That's a delta V V, no. Anyway, delta V we computed in the last step, and we said it was QD over A epsilon naught. Well, we're ready to go. We're ready to take that that ratio. It's pretty easy to do. We go C is the Q, that's the Q, over the V, which is QD over A epsilon naught, and that is equal to, the Q's are going to cancel, and this thing is going to flip upside down, and we get the capacitance of our parallel plate capacitor is A epsilon naught over D. And so what that tells us, and this is intuitively it makes sense, or at least some of it does, it means that bigger area means more capacitance. And that lines up with what we talked about earlier, because you can put more charge on without running up the delta V. And it also means that when the D gets smaller, that also increases the capacitance. So the closer you can put the plates together, the larger the capacitance is of the configuration.